Hey everyone, in this video, we're going to be creating a neural network completely from scratch, without PyTorch, without Tensorflow, just plain old Python and NumPy for mathematical operations. So I hope you're as excited to get started as I am, because neural networks are extremely important in the field of artificial intelligence. They allow us to model and learn relationships between inputs and outputs in incredibly complex ways. They're used in fields such as medical diagnosis or autonomous driving and in countless other areas. And it's something that everyone should learn about or at least be familiar with. So just to give you a quick lay of the land here, the first thing that we're going to do is go over the data set. What are we trying to predict with our neural network? Second, I'll go over what a neural network even is and the math behind it. And finally, we'll actually code the network from scratch. So first, let's talk about the dataset. This is called the digit recognizer dataset on Kaggle. It's basically the MNIST dataset, which is a fundamental and incredibly beginner and important dataset in the field of computer vision. It consists of handwritten digits from 0 through 9, a bunch of images of them. For example, the training file has 42,000 images of digits, and these images are 28 by 28. So 28 times 28 equals 784 pixels. So let's take a look at what the data actually looks like. If you take a look at the training data set, we have the first column, which consists of the label, and every other column after that is pixel 0 through pixel 783. Now, these pixel values can be any value from 0, which is black, to 255, which is white. So any value in that range. So basically what we're going to be doing is we're going to be inputting the pixel values into our neural network and trying to predict the correct label. And then we'll compare our predicted label with the actual label and find an error rate, or a loss as we call it, and use it to train our neural network and adjust the parameters in our neural network to basically guess the correct label more often than not. And we do this iteratively, and it takes some time, but our neural network will get better and better. So let's talk about what a neural network even is. Neural networks are made of neurons. They're basically modeled after our brain. So what we have here is an input layer of neurons, and what this layer does is it takes in our input, it feeds it to hidden layers, which then feed out to output layers. So each neuron in each layer is connected to each neuron in the next layer, and each connection contains weights. These are parameters that we want to be learning and tuning so that we get the correct outputs. So basically, the data flows through the network and gives us an output. So this is called a multi-layer perceptron. And the reason why it's called a multi-layer perceptron is because each neuron is known as a perceptron. They were invented by Frank Rosenblatt in 1958. And each node has biases. So along with the connections that contain weights, we have biases. So how each perceptron works is it takes an input and it multiplies the input by the weight of that connection. And as you can see, each neuron here has multiple connections backwards. So we take the inputs and we multiply by the weights of each connection. We sum the weights and the result together. And then we have a nonlinearity, which is an activation function. So we'll talk more about activation functions soon, but basically that gives us our output. So each neuron has an input and an output, and the combination of these inputs and outputs give us a final output, and it works incredibly beautifully. So what is our neural network going to be like? What is the size of it, and how is it going to work? Well, the first layer is going to have 784 neurons, or 784 inputs. And the reason why is because the images are 28 by 28, which contains 784 pixels. So we need 784 inputs, one for each pixel. Our intermediate hidden layer, which is basically The definition of a hidden layer is, it's called hidden because we don't interact with it directly. It's just part of the neural network, and it gets inputs and it gives outputs, but we don't interact with it. So technically you can choose any value you want for how big you want your hidden layer to be. But in our case, we're going to use the value 128, just some value in between 784 and 10. And the reason why we have 10 is we have one neuron for each digit it could possibly be, 0 through 9. So if it was a 0, this neuron would activate. If it was a 1, this neuron would activate. If it was a 9, this neuron would activate, and so on. So now let's talk about activation functions. Basically, neural networks are modeled after our brains. In our brains, we have neurons that fire and pass that impulse, pass that action potential through their axons, and then fire other neurons. So neurons firing affect the firing and activation of other neurons. So what activation functions do is, basically what they do is, we say that if the output of a neuron is a specific value, if the summation is a specific value, we take that value and pass it through an activation function. And if it is a certain value, then the neuron activates. So what we can have here is a simple step function where we say that if the value is negative, then don't fire the neuron, don't activate the neuron, don't pass on the output to the next neuron. That's what not firing means. And if it is a positive number, then we give the value of 1. So the output of the neuron would be 1. There are a variety of activation functions. So we can have tanh, which is basically looks like this curve. It passes through the origin, and this is its equation here. We can have rel-u, which is the algorithm that we're going to be using, where we say that if it's a negative number, the neuron should have 0. It shouldn't activate, shouldn't pass on any important value to the next neurons. But if it is a value more than 0, then pass that value to the next neuron. We can also have sigmoids, which are for binary classification uses. If we want to classify, for example, yes or no, or 0 or 1, or a cat or not a cat, or a dog or not a dog, something like that. And this is generally used in the final layer, in the output layer. We're not going to be using this, and the reason why is because the MNIST dataset, we want to be predicting from a variety of classes, 0 through 9. So we're not doing binary classification. Instead, we're doing multi-class classification. So our final layer activation function is going to look like this softmax function. And it looks very similar to the sigmoid, but it has a different equation, which is here. The reason why this equation would be much better than the sigmoid in the case of multi-class classification is when it interacts with our loss, our error rate equation, it basically simplifies into something that's very simple to work with mathematically. So what the softmax basically does is it takes an output layer. So for example, we have outputs 0 through 9 for each digit, and each neuron is going to have its own value. And what we do is each value passes through the softmax function and gives us probabilities that add up to 1. So next, let's talk about the dot product. The dot product is basically how we multiply our weights with our inputs. This is different from matrix multiplication in linear algebra. The dot product, even though it looks like a multiplication, is a totally different concept from vector or matrix multiplication. So how the dot product works is we sum up the values of, for example, if we had a vector 1, 2, 3, and we had another vector 2, 3, 4, what we're doing basically is we're multiplying this with this, this with this, and 3 with 4, and then adding up the value so that we get a scalar result. And this is what that basically represents. So the dot product can also be written as a way of matrix multiplication. So we represent vectors as column vectors. So in matrix multiplication, we multiply each row with each column, which is why we're basically taking a transpose. This T is called a transpose. We take the column vector and we flip it diagonally to make it into a row vector. And then we use matrix multiplication to multiply the row with the column. And we get this scalar value because 1 times 4 is 4, 3 times -2 is -6, and -5 times -1 is 5, which adds up to 3. And an important thing to note here, and this will basically dictate when we transpose and why we have to transpose, is because when we multiply vectors or matrices, we have to be careful about their dimensions. So we have m by p, so we have a vector that's m by p, for example 1 by 3, and another vector which is p by n. What this means is that the inner dimensions of the matrix, if we had 1 by 3 and 3 by 1, this works because the inner dimensions have to match. For example, if we had 1 by 4 and 3 by 2, this wouldn't work because 4 and 3 don't match. So what will happen is the inner dimensions have to match, and then once they get multiplied, they result in m by n size matrix. So this 1 by 3 multiplied by 3 by 1 would become 1 by 1, and this would become a 1 by 2. So that hopefully that makes sense, because as you can see, when we have this 1 by 3 matrix and this 3 by 1 matrix, the dimensions match here, and it also becomes a 1 by 1 result, which is just a scalar, a 1 by 1. So now let's talk about the training process of our neural network. How does our neural network get better as time goes on as we train it? So the first thing that we have to do is take our inputs and get outputs from it, so that we can later evaluate those outputs and then do a backward pass to make those outputs better by tuning our parameters. So the process of getting the output from the input is called the forward pass. So here we're going to represent A0 as X. This is our input here. The Z1 is going to be the weight times the input plus the bias. That's how the perceptron works. We take the inputs, the weights, plus the bias, where each node has its own bias and each connection is a weight. We take it, and the first layer is going to be the weight times the input plus the bias. Then each node is going to have an activation function. And since we only have one hidden layer, we only have one activation function of rel_u. And then in the final output layer, we take the weights and we take the output of the previous layer, and then we add the biases from the second layer, which is the output layer. And then after that, we finally do a softmax. So this is how the input gets transformed into our output. So now let's talk about our backward pass. Training neural networks at its core is gradient descent. It's one of the main algorithms for training neural networks. And what gradient descent is minimizing loss, minimizing our error by adjusting the weights and adjusting the biases. So this is what our loss function looks like. What even is a loss? It's our error rate. So what we're doing is we're taking the actual output value, multiplying it by the log of the predicted value plus some small value epsilon, taking the sum of that, since each of these are vectors, we sum all the values in the vector, and then we divide it by the number of elements in the vector. So this particular loss function, there are a variety of loss functions, but this particular one is called cross-entropy loss, and it interacts really well with softmax in our output layer. It basically simplifies down really well with the combination of softmax and cross-entropy. And the benefits of cross-entropy loss is that the outputs are non-negative. It reaches 0 when there's an exact match between the predicted value and the actual value, when they match, the result of the loss is 0. And the cross-entropy loss heavily penalizes confident wrong predictions. And since it's differentiable, it helps us do gradient descent. Since what gradient descent is, we're basically taking the derivative of each value, each weight, each bias, and seeing how it affects the loss, so that we know how to tune our weight and our bias so that the loss gets minimized. And I'll talk more about that very soon. So at a high level, what gradient descent is doing is it's taking a weight and it's assigning the weight minus this alpha, which is some value, times the derivative. So a whole lot of math. What does that even mean? So we take a learning rate, commonly 0.1, 0.01, something like that, 0.001. And it's basically how much are we tuning our weights at each step. And we set that value. That's called a hyperparameter. We're setting that value manually. And we're saying take this much of a step to tune the weights. Now, what this derivative is how much does the loss change when we change the weight. So, for example, if we change the weight positively and the loss changes positively, then this derivative is positive. If we change the weight positively and the loss is negative, then we have a negative value for the derivative. So if we had the case where the weight was positively changed, when this derivative is positive, which means that when we minimize the weight, the loss minimizes, or at the same time simultaneously, when we increase the weight, the loss increases. So our goal is to minimize the loss. So to minimize the loss, if we had a positive derivative here, what we need to do is also minimize or decrease the weight, which is why we minus here. So what we're saying is that when we subtract it, the loss gets subtracted as well. On the other hand, if we had a negative derivative where we minimize the loss by maximizing the weights, then this value would be negative, so we would end up increasing the weight, which means we minimize the loss inversely. And we do the same thing with biases. So this basically gives us the value and the direction of which we need to change the weights. The learning rate tells us, this learning rate alpha tells us how much we need to change, how much we want to change the weight by manually setting that value. And we're basically taking the weight and subtracting this and setting it as our new weight. And we do that same thing for the bias as well. So let's go through some of the math for the output layer. We have this basic formula for how we adjust our weights, and it applies for both the output layer weights and the hidden layer weights. So with our output layer weights, we basically want to find this derivative so that we can update the weights accordingly, and we want to do the same thing for the biases, and we do it for each layer, the output and the hidden layer. So first, let's find the derivative of the loss with respect to W, the weights, for the output layer. What does that look like? We use the chain rule. What the chain rule is it tells us how to find this derivative. Since we don't have an exact correlation between the loss and the weights, what we do is we find the correlation, the loss with respect to Z2, and multiply it by the derivative of Z2 with respect to W2. And as you can see, these cancel out and we get this result. But since we don't have the value of this, we have the values of these two. So we basically simplify it and calculate the derivative of the loss with respect to W2 from these values. So what is the derivative of the loss with respect to Z2? This is what it looks like here. It's the average of the prediction minus the actual values. So to get this, we would technically need we would need to do the chain rule on that as well. But because softmax combines with cross entropy loss really well, we skip the step and we get this value. You can do this derivation on your own, but for now, just keep in mind that the derivative of the loss with respect to z2 is just this value, though you can solve it on your own if you want. And then we find the derivative of z2 with respect to w2. And how do we do that? We go to z2 and we find the derivative with respect to w2. So w2 times a1 plus b2. We take the derivative of that with respect to w2. We treat this as a constant, and we treat this as a constant, and we get this as a result. That's just how you take the derivative. If you don't know how to take a derivative, watch my video on calculus for math for machine learning. So we get the result that the derivative of the loss with respect to w2 is this value here. Now let's do the same thing for the bias. We have dl with respect to dz2 over db2, and we already know this value. It's just from here, right? So we carry that on, and then we do the same thing with respect to db2, this. So we go over to z2 and we take the derivative with respect to b2, and it's just 1 because this cancels out since it doesn't have a coefficient, and these are just constants, so they cancel out too. So we're left with 1. So obviously when you multiply with 1, you get this as this remains. Now we do the same thing here for the hidden layer. It's the same process, although one thing to note is that we have to take the derivative of rel u, and the derivative of rel u, since the formula of rel u is when it's less than 0, it should be 0, and when it's more than 0, it should be x. The derivative of that is when it's less than 0, it should be 0, and when it's more than 0, it should actually be 1. So hopefully that all makes sense. So now that we went over all the math involved in training our neural network, we went over what a neural network even is and how we get from the input to the output. We went over activation functions and also what our specific neural network is going to look like. Let's get to coding it out. All right, so the first thing that we want to do is we want to load in our data, and we want to split it into x and y, the input and the output, since the training set contains both the input and the output. And we also want to split it into a training and a test. So the Kaggle contains a separate test file, but that test file doesn't have labels with it. Basically what you do in Kaggle is you submit your predictions of the test set, and Kaggle will automatically evaluate it for you. But because that doesn't have labels, we're just going to take the training file from Kaggle and split that into a training and test set so that we can find the accuracy from the labels for the test set as well as the training set. So let's get started. So the first thing that we're going to want to do is import our library. So we're going to import NumPy for our mathematical operations. We're going to import pandas. The reason why we're importing pandas is for handling our data as well as splitting it into input and output. It's basically for file handling and data handling. And then we're going to want to import matplotlib pyplot just to plot out some of our results and visualize them. So the next thing that we're going to want to do is actually load in our data. So how do we load in our data? What we do is we use this function from pandas. Pandas.readCSV, since our data is in the CSV format. And the file that we're going to be using is data.csv. Make sure it's in the same directory as the file that you're working with. So if you're coding in a Python file or an IPYNB file, make sure your data is in the same folder, or if it's in a different folder, you can just put the path to it inside here. So the next thing that we want to do is let's look at what shape our data is actually and how much data we have. and it's not defined. Yeah, so I have to run this, and then we run this, and then we see that we have 42,000 different examples, different images, and 785 different columns. So we have 784 for each pixel, and then 1 in the beginning for the actual label column. So we want to split our data into a training set and a test set. So let's say train data, go to data iloc. So we use data iloc, and iloc it basically means integer location, and we specify that we want all of the values, all of the rows up till 33,600. And the reason why we want 33,600 is because that's 80% of 42,000, and we want 80% of the data to be in our training set and 20% of the data to be in our test set. We don't want to use much more in our test set because then we won't have enough data to train on, and if we have too little in our test set, we're not evaluating thoroughly enough. So we do the same thing with the test set, and we say everything after 33,600. The next thing that we want to do is we want to split it into x's, which are the actual pixel values, as well as y, which are the labels. So we want to take every single row, which is this colon, and we want to take all the values after the first column. Since the first column is the label, that's going to be our y. And an important thing that we need to do is normalize our pixel values. And the reason why we're doing this is because each pixel value is in between 0 and 255, but we don't want large values. We want to squeeze it to be between 0 and 1, so 255 becomes 1, and for example, the value in between 0 and 255 becomes 0.5, and this way our data becomes a lot simpler and we don't have to deal with large values. So we do the same thing with y train, with the 0th column, the first column, which is the label column, and we do the same thing with our test data. Right, so this should be right. So let's print out what it looks like. So we have 8,400, which is 20% in our X test, as well as 8,400 in our Y test. But X test has 784 values, each pixel value, and Y test has 1. There's an invisible 1 here. It's technically a 1D array. If it was written 1 here, that means it would be a 2D array, but basically it's 80,400 examples of one label. And another important thing that we need to do with our data is called one-hot encoding. So what one-hot encoding is instead of representing our data as labels of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, instead we have an array of zeros. So let's say we had the values in between 0, 1, and 2. We had those values in our training set. Let's just take that as an example. If we wanted to represent the value 0, we'd put a 1 here. If we wanted to represent the value 1, we'd put a 1 here. And if we wanted to represent the value 2, we'd put a 1 here. So this is called one-hot encoding. We basically stretch each label into a representation where there's values of 0 and a 1 wherever that specific label index is. So how we do that is we do y train encoded, and we do npi 10 y train. So what this is doing is np.i10 is going to give us a 10 by 10 array where there's ones along the diagonal. So the 0th one would have a 1 in the 0. The first the second row would have a 1 in the second column. The third row would have a 1 in the third column, and so on. And when we index this y train, we basically are saying that for each label, take the specific one-hot encoding and then generate 8,400 different examples of those one-hot encoded vectors. So then we have to do the same thing with it in the test set as well. So this is our data handling, and it's basically done. The next thing that we're going to want to do is, remember that we said that the input size of our neural network, we want it to be 784 pixels. So let's say input size 784. We want the intermediate layer, the hidden size, to be 128 and the output size to be 10. So let's just set those values now. Now let's create an instance of the neural network class that we'll create later, but this is basically the boilerplate or the implementation of the high level, and we'll implement the actual neural network details later. But let's say nn is equal to neural network, and we pass in the input size, the hidden size, and the output size. There's an underline here because we haven't implemented it yet, but basically we want to take that neural network and we want to train it. We're going to implement a function called train, and in that function we're going to pass in the xtrain, ytrain encoded as one-hot vectors. We're going to specify the number of iterations or epochs, which is 50, a learning rate, remember alpha, the value alpha, as 0.1, and a batch size, which we'll talk about later, which is going to be 32. So now let's actually code out our neural network. So we have a class called neural network. We're going to initialize it. It's going to take in, as we specified before, input size, hidden size, output size. Then we set some attributes for the class: input size, hidden size, and output size. Now we also want to specify what the weights are going to be. So when we initialize our weights, we are not initializing them as 0. We need to initialize our weights with random values. And the reason why we do this is if we specify them to be all zeros, then they would end up doing the same thing. They would all behave in the exact same way since they started from the same place. And in doing so, we lose all the beautiful complexity inside our neural network. So what we're going to do is we're going to use a specific method called Kaiming-Hay initialization, invented by Kaiming-Hay at MIT. And it's a specific way of initializing random weights. We're going to multiply it by the square root of 2 over self input size. Now we're going to do the same thing with the weights of the first hidden layer as well as the weights in between the hidden layer and the output layer. But first let's initialize the biases of the first hidden layer. And keep in mind the input layer doesn't have any weights or biases. The weights start from the connection from the input to the hidden, and the biases start from the first hidden layer. So for our biases, we can actually, it's totally fine to just initialize them as zeros. So that's what we're going to do. Now we do the same thing for weight 2 and bias 2. Now let's create the train function that we're using to actually train our neural network. So as below and as in the cell below, we're using these parameters for the train function, the x, the y, the epochs, the learning rate, and the batch size. We're going to say for epoch and range epochs. Since we're going to be training for a specific number of iterations, in each iteration we're tuning our weights, and we're going to do it multiple times for multiple epochs. We're also going to say specify the batch size, and what we're doing here is we're using something called mini batch gradient descent. We talked about gradient descent before. There's a few different types. The main types are mini batch gradient descent, batch gradient descent, and stochastic gradient descent. In our case, we're going to use mini batch. Basically what we're doing is we're splitting the training set into miniature small batches. And what batch gradient descent does is it uses the entire data set at once. And what stochastic gradient descent does is it uses one example at once. So there are some advantages of mini batch, which is it avoids local minima in the loss function, which results in more robust convergence. It's more stable and it requires less memory than batch gradient descent, which uses the entire data set. Batch gradient descent has stable convergence as well, but it's really slow for large data sets, and it can get stuck in local minima in the loss function. To implement it, we would just remove this batch size. We would just not use it at all. For the stochastic, it's faster because it uses a single example at once, but it won't converge to the exact minimum in most cases because it'll have a high variance in model parameters. So to implement that, we would just set the batch size to one example at a time. But since we're using mini batch, what we're going to do is we're going to specify the batch size, which here is 32. And we're going to say take from x up to a size of a batch, that's the batch size. We do the same thing for the y batch. Now, what we're doing here is we're saying that do a forward pass, which is basically getting the output from the input. And that's going to be our output so that we can train based on the outputs later. And we'll implement this forward function in a bit, but for now, this is what we have. We also want to do a backward pass, which we'll also implement later, and it's going to take the x batch, y batch, the output, and the learning rate. And we also want to print our progress every 10 epochs, just so we can take a look at what the loss looks like for every 10 epochs. So the cross entropy loss looks like this. It's the mean of the sum of y times the output. It's the same equation that I showed you before, plus a small epsilon. And the reason why we add a small epsilon is to avoid log 0. If we did log 0 here, it would be undefined, and we don't want an undefined value. So that's why we add the small epsilon. And cross-entropy loss basically measures the performance of the classification model. And the classification model's outputs, because of softmax, is going to be a probability value between 0 and 1. So we also want to keep track of the accuracy so that we can print that as well. So the accuracy is just from the probability values, we want to take only the argmax, which is the highest value in the probability values. For example, if we had 0 through 9 and each of them had a value, we're not predicting for them to be multiple values. We only want to choose one value. So we choose the one that was activated the most, which is what argmax does with the output. Then we're going to print what it looks like. And just a little kink here, what I'm going to do is print the final results one more time. And the reason why is because we're going to go from epoch 0 to 49, because we have 50 epochs, 0 through 49. And we're going to print out the results for everything that's divisible by 10. So we have 0, 10, 20, 30, 40, but we don't have 49. So which is why I'm going to print out the final results here. This will print out the results of the 49th epoch. And the final thing that we want to do is create a function called predict, which will basically just be a forward pass, getting our output from an input. That's our prediction. So now let's actually implement the forward pass and the backward pass. To start with forward, we're going to say self.z1. It's the same equations that I specified in the on my iPad, where I showed you the actual equations for the forward pass and the backward pass. But here's what it looks like. And here's the rest of it. Rel for the first hidden layer and softmax for the output layer. And we're just doing a dot product between the weights and the biases. And we're adding the biases. Sorry, we're doing a dot product between the inputs and the weights, and we're adding the biases here. We need to implement rel and softmax, so let's do that. Rel is just going to be pretty simple. We're just going to return np maximum 0 for x. If the value of x is less than 0, then 0 is more than that, so we return 0. Or if it's more than 0, then we just return that value. We also need to take, we also need to implement softmax, and the equation for softmax is here. This is the equation that I showed you before, and the reason why we're actually subtracting the max, which is something I didn't show you, is because we want numerical stability and to avoid getting a huge positive number after exponentiating. If you look at the graph for e to the power of x, basically goes as the values increase of the x, it grows rapidly, and we don't want huge values for even a moderate positive number. So we are subtracting the max value here just to keep the value small. Okay, now let's implement the backward pass. So we want the batch size to be x.shape 0. The output layer is going to be just the output, the predictions minus the actual y values. Then we take the derivative of the loss with respect to W2. And the reason why we're doing transpose here is because the A1 initially has the shape batch size, comma, hidden size, and delta 2 has batch size, output size. So because the first one's batch size, hidden size, we want to flip it so it's hidden size, batch size, so that the inner dimensions match, the batch sizes of the inner dimensions match. So that's why we're transposing. Now the derivative of the bias is going to be here. It's the same equation, so I'm just going to copy and paste what it looks like. And we need to implement the derivative of rel u. So we'll do that after we put in all the derivatives. And the reason why we need all of these values here, d1, dw1, db1, the same for 2, is because we want to update the weights and biases with this method here. So let's implement the rel u derivative. So we could implement it how it looks in gray, but there's a better way using NumPy. Instead, we just return np where x more than 0, 1. If it's not x more than 0, then return 0. So now we have the entire training process of our neural network done. Little bug here. Let me just fix this. Okay, so I found the bug. The problem here is that for weights, we had it previously input size, hidden size. Instead, we want hidden size, input size. Output size. There we go. Another bug. Okay, great. So I think this is a problem here. We want it to be hidden size instead of input size. Okay, another problem. This has to be output size here. Great, now it works. Except we're getting a bunch of epochs, so actually this has to be back here. So let's try changing this to x.shape 0. No, didn't work. Right, so the problem here is because we want the epoch to be here. Some indentation errors. There we go. I think that should be working. While it's training, let's just write some more code. So after it's done training, we actually want to evaluate the model. So we want to evaluate the accuracy of the model. So let's do predictions equals nn.predict, which we wrote earlier. Predicted labels is equal to np argmax, and accuracy is equal to this np.mean. We want the mean of the predicted labels wherever it equals the y-test, and we can finally print the test accuracy. Now I'm going to paste in some code to visualize our results. So we've written the code where we print the test accuracy, and we'll also see some visualizations of our predictions as well as what the labels actually are. And I'll also put some visualization of where our predictions are actually incorrect, so we can see why the model's making mistakes and where it's making mistakes. For example, thinking of 2s as 5s or something like that. So I'll see you when it's done training. Great, so it's done training, and we have a final accuracy of 100%. And you may find it a bit odd that even in the first epoch 0, it has an accuracy of close to 94%. And the reason why that is because we're doing forward and backward pass multiple times because we have batches of 32. We're doing it multiple times even before printing out the accuracy of the 0th epoch. So because we did it a bunch of times, we get an accuracy of close to 94%. So now let's predict and get the accuracy of our model on the test set. So we'll see probably a difference. We'll see a few percentage points decrease between the output of the training accuracy and the test accuracy. If there's a large difference, that's what's called as overfitting. What's basically happened is that your model has become trained very well on your training set, but it's overfitted to your training set and it won't generalize well to test set. So basically has memorized the values in your training set and doesn't know anything new or much new. So let's print out the training accuracy, the test accuracy. It's 97.5, close to 98%, pretty good. And let's visualize what our predictions look like. So here we have predictions that are all true. And let's also visualize predictions that are false. So the actual number here is 2, but we predicted 6. This is where we can blame the handwriting and not our model. So the true is 5 and the prediction was 7. This looks kind of like an 8, but it's actually a 0. This 1 is pretty thick, so the model thought it was an 8, but it's actually a 1. And this 7 is pretty skinny, so it thought it was a 1, but it's actually a 7. So now we've created a neural network completely from scratch using just NumPy, doing some data handling with pandas, and plotting our visualizations with Matplotlib PyPlot, but the heavy work is being done by NumPy. I hope you enjoyed the video, and I hope you learned quite a lot. Thanks for watching, and I hope to see you soon. Cheers.